A regular hexagon is a polygon that has 6 sides with equal length and 6 interior angles with equal measure. In figure 1, regular hexagon has side length 2x, and its vertices lie on the circle with center O. Diagonals divide it into 6 congruent equilateral triangles. In terms of x, what is the radius of the circle? All right, so we're looking at this guy right here. All right, so it's equilateral, right? That's a huge helpful point, because if the side is 2x, so this AB is 2x, then this is 2x, and this is 2x. And that is the radius, right? OB, so therefore the radius is 2x. So I guess that's pretty much all you need to do. And you can also do it a little bit longer by looking at internal angles, right? Because they talk about internal angles. The internal angles of a hexagon would be 120. So for example, that angle right there, this angle right here, this angle right here, those are all 120s. Now since this line would cut that internal angle in half, this would be 60 and that would be 60. And similarly, that would be 60. And so even if they didn't tell you that they're equilateral, you could figure it out just by calculating the angles. Okay, so that's 2x. The midpoint of side AB is labeled M, as shown in figure 2. In terms of x, what is the length of OM? Okay, so I'm going to draw it here just to kind of exaggerate it. So this is an equilateral triangle, correct? And then they've drawn this line. But then if you notice very closely, they've put these symbols, and that basically means that, you guys know, those are equal. If those are equal, and this side is also the same as that side because it's equilateral, then by the definition, this will be a right angle. That's basically how it works with triangles if you have equilateral or isosceles. So now we can figure out the angles. Previously, I did the work for you, and we figured out that was 60 degrees, and therefore this would be 30, since the angles all have to add up to 180, right? Okay, so then the 30, 60, 90 triangle is what we've basically created here. And as you guys know, for the 100th time, the ratio of the sides of a 30, 60, 90 triangle are 1, 2, and root 3. And we know already that this side is 2x, so therefore from here to here is x, and therefore this side right here would be root 3x. That's essentially calculated by that ratio. So root 3x is the answer there. In terms of x, what is the area of the hexagon ABCDEF? Okay. Well, the hexagon consists of 6 equilateral triangles, right? And the formula for area of an equilateral triangle is, some of you may remember this, it's actually very helpful to know it. It's root 3 over 4 times a squared, where a is the length of a side. So if you plug in, what is the length of the side? 2x, right? Yeah. So you plug 2x in there, so you get the 6, because there's 6 of them. And then the area is root 3 over 4, 2x all squared. And then when you crunch out these numbers, you will get 6 root 3 x squared. Because they want it in terms of x, right? Because we don't know the value of x. And then finally, the region that lies inside the circle and outside the hexagon is shaded. The area of this region is 123. To the nearest tenth, determine the value of x. Okay, so now we're working with this guy here, figure 3. So the shaded region, shaded area, let's just call it shaded area, is the area of the circle, which would be pi r squared, minus the area of the hexagon. So I'll just put hexagon right there. Okay, well, they told me in the question that not the surface area, the shaded area is 123, and then pi, well, r we had previously figured out was 2x, and then the area of the hexagon we previously figured out was 6 root 3 x squared. So that's basically the algebra, and then we have to solve for x to the nearest tenth. Okay, so 123 is, what is this going to be? 4 pi x squared, and this doesn't really change. Factor out the x squared, and then put what's remaining on this side, so that's going to be 4 pi minus 6 root 3. And then you guys can do this and calculate this. You're allowed to use calculators in the Canadian exams, and when you do, you'll get approximately 7.528, and then rounded to the nearest tenth, it'll be 7.5. So with 1 kg of muffin batter, exactly 24 mini muffins and 2 large muffins can be made. With 2 kg of muffin batter, exactly 36 mini muffins and 6 large muffins can be made. With 2 kg of batter, exactly 48 mini muffins and n large muffins can also be made. What is the value of n? Okay, so I guess we just have to do a comparison of these two pieces of information. So with 1 kg, let's just put it here, muffin batter, and then we got mini and large. So this is 24 and this is 2, and then let's see if I can, I think I can pretty easily figure this out, because if I double this, I get 2 kg, and this would double to 48, and this will double to 4, and that's pretty much what they're saying. So they're saying n large muffins, well, it's 4, and I think that's it, n equals 4. Okay, so far so good. Let's move on. With x kg of muffin batter, exactly 84 mini muffins and 10 large muffins can be made. What is the value of x? Okay, so let me see here. I could probably have to do a little bit of a combination this time. 84, how do I get 84? Okay, so with 1 kg was 24 and 2, right? With 2 kgs, let me go by what they say in the question. 36 and 6. Yeah, 36 and 6. So 36 and 6. Now, how do I get 84? If I do 2 of these guys, yeah, I think if I do 2 of, and then I add it all up, this will be 84. 48 plus 36, yeah. Okay, so I got my 84, and this is 1 plus 1 plus 2, which is 4 kg, and this is 10. So what are they asking for? Oh, they're asking for how much muffin batter. Okay, so 4 kg of muffin batter to get 84 and 10. Yep, okay, and we're moving right along to C. Determine how many mini muffins can be made using the same amount of batter that is needed to make 7 large muffins. Okay, so again, manipulation of the pieces of information they gave us in the question stump. So we got 2 kg was 36 and 6, right? So we got to get 7 large. So I've got to try to manipulate that number into 7. So how do I do that? I guess multiply it by 7, and then divide by 6, right? So if I multiply this by 7, I get 42, and then if I divide by 6, I get 7. So I've got the 7, and then we'll see what numbers come over here. This is 252, and then that would be 42 if I apply the same operations of multiplying by 7 and dividing by 6. And the 2 would be 14, and then 14 over 6. And what do they want? They determine how many mini muffins. Okay, so that's just the 42 is what they're asking for. A sequence is created in such a way that a real number is chosen as the first number in the sequence, and each of the following numbers in the sequence is generated by applying a function to the previous number in the sequence. For example, if the first number in the sequence is 1, and the following numbers are generated by the function x squared minus 5, then the first 3 numbers in the sequence will be 1, negative 4, and 11. Since 1 squared minus 5 is negative 4, and negative 4 squared minus 5 is 11. The first number in the sequence is 3, and the sequence is generated by the function x squared minus 3x plus 1. What are the first 4 numbers? All right, shouldn't be too bad. So we've got the first number is 3, and the second number would be taking this function and substituting 3, so it would be 3 squared minus 3 times 3 plus 1, and I believe that is 1. Okay, and then I take that 1 and put it back into this function, so it would be 1 squared minus 3 times 1 plus 1, And that is -1. Yeah, -1. And then finally, take that -1, plug it back into the equation. So it'll be -1 squared minus 3 times -1 plus 1. And that looks like, to me, 5. So those are the first 4 terms: 3, 1, -1, and 5. Part B, the number 7 is the third number in a sequence generated by the function x squared minus 4x plus 7. What are the all possible first numbers? Okay. Okay, so the first number we don't know, the second number we don't know, but the third number we know is a 7. Okay, so that means that this function generated a 7, right? So let's just say this was an A and this is a B. I don't know the numerical values, obviously. So what it basically means is that, yeah, it means that b squared, what is the function again? Minus 4b plus 7 is equal to 7. Correct? That's how you would get the 7. Okay, so that shouldn't be too big of a deal. That means the b squared minus 4b is equal to 0. So that means if you factor out the b, you get, let's see here, you get b minus 4. So b is either equal to 0 or 4. Okay. B is equal to either 0 or 4. All right. That's a pretty good finding. Now we have to figure out a. So the a is going to be calculated in the same story, but now we have two choices. So either a squared minus 4x plus 7 is 0, or a squared minus 4x plus 7 is 4. Correct? Okay, so for this guy, oh boy, I gotta do a quadratic, right? Because I don't think this factors. All right, so what's the discriminant, first of all? B squared minus 4ac. Let me just see here. That's going to be 16 minus 112. Is that right? Yeah. So that actually is less than 0. So there's no real solutions because there's something about real in here, I think, something. Yeah, a real number. So we're not going to get a real number, so that has no solutions. So I guess we're only left with this guy. So this is going to be a squared minus 4x plus 3. And when I add that factor, so that's good. So we got a, oh, sorry, I'm mixing a's and x's here. Sorry about that. A, 3 and 1, negative. So a is either 1 or 3. Is that right? Yeah. So what are they asking for again? Yeah, the possible first numbers. So the first numbers are either 1 or 3. And yeah, I think that pretty much covers it. The first number in a sequence is c, and the sequence is generated by the function x squared minus 7x minus 48. If all the numbers in the sequence are also equal to c, what are the possible values of c? Okay, so the first number is c, and the second number is c also, but that's obviously generated from that function, so you'd have to take that initial c and plug it in that function. So something like that. Yeah. Okay, so I guess I just have to solve this. So this is going to be c squared minus 8c minus 48. And does this factor? C, 12 and 4. 12 and 4 would be 48, but then it would be negative. Hold on here. Negative and positive, I think. Yeah. Yeah, I think that's it. So c is either 12 or negative 4. Okay. Sounds good to me. All right, let's go. Last one. A sequence generated by the function x squared minus 12x plus 39 alternates between two different numbers. That is, the sequence is a, b, a, b, a, b, and so on, with a not equal to b. Determine all possible values of a. Okay, so according to the so we have the first number, the second number, the third number, fourth number, and so on, right? So let me see here. The first number is a, and then the second number would be a substituted into there, so it would be a squared minus 12a plus 39, and that would be equal to the second number, which they have designated as b. And then the third number, again, you'd substitute it into that equation, and that would be equal to a, because this is the first number, this is the second number, and this is the third number. And then it just keeps on going like that. But I think these two equations are sufficient. Since we have two equations, two variables, we can figure it out. Okay. So boy, I'm trying to think what's the best way. Let's keep it simple. If I just subtract them, take that second equation and subtract from it the third equation, I'm going to get this a squared minus 12a plus 39 minus that b squared minus 12b plus 39, like that. And then on that side, it will be b minus a, right? Okay, so a lot of this stuff hopefully will cancel. This will be a squared minus b squared minus 12a plus 12b, and the 39's cancel, so not as much as I'd hope, but then we just get that b minus a, and then put everything on one side. A squared minus b squared minus 11a plus here. Hold on a second. I gotta make sure I don't rush this. Minus 12a, you're gonna add a to minus 11a, I was right, and then subtract b plus 11b is 0. Okay, this factors a minus b, a plus b, I think the 11, that's pretty obvious, a minus b, and then finally the a minus b factors, and then you'll be left with a plus b minus 11. Okay, so that means that a minus b is either equal to 0, so that means a equals b, but they told me that a does not equal b, so this one is not possible. So the only other thing that's possible is that a plus b minus 11 is equal to 0, so therefore a plus b is equal to 11. Okay. All right, so where do I go from here? I guess I just have to substitute at this point, because I have this, right? So that means that b is equal to 11 minus a. Okay, so then I can put it back into one of these equations. Let's put it back into that guy. So a squared minus 12a plus 39 is b, but b is 11 minus a. Okay, I got it. And then I just solved this. Okay, so a squared, we're adding, so minus 11a, and then this will be 28. And I'm pretty sure this factors very nicely. So we have a 7 and 4 minus minus. So a is either equal to 4 or 7. And there you go. Every integer n greater than 1 can be written as n equals p to the power of a, p2 to the power of a2, and so on, where k is a positive integer, and p1 is less than p2, and so on, and they're all prime numbers, and a's are positive integers. For example, 1400 is 2 to the power of 3 times 5 to the power of 2 times 7 to the power of 1. The number of positive divisors of n is denoted by f at n, and it's known as f at n equals 1 plus a1 times 1 plus a2, and so on. How many positive divisors does 240 have? That is, what is the value of f240? Okay, so some of you are familiar with this, some of you are not, but I'll just show it to you. I'll just start with their example. So you take any number, right? Let's say this example that they gave me, and you break it up into its prime factorization. So in this case, it's 2 to the power of 3 times 5 to the power of 2 times 7 to the power of 1. And then if I asked you how many positive divisors there are, they're giving you a definition, and basically what it means is you just take that exponent and add to it 1. They're putting the 1 first, interestingly, that's fine. And then you take that guy, which is the next exponent, you add 1. And then you take that one, and you add 1 to it. And then you multiply them all. And this is going to be 4 times 3 times 2. And if my math is good, that's 6 times 4, which is 24. Okay, hopefully that's right. And what that means is that there's 24 divisors of this. Now, you could have done that manually, but that obviously takes a long time. And if this number was bigger, it would take forever. So when you have this system, it makes it more efficient in terms of time. So now we got to do the same thing for 240 here. Okay, not a problem. So 240, the first step is to break it up into its prime factors. And I believe 240 is, you just do this within your calculator. You say divide by 2, and then divide by 2, and so on, because you may not even know. So it's that. And then, of course, if you write it grouped together, it's 2 to the power of 4 times 3 to the power of 1 times 5 to the power of 1, right? So according to the definition, the f at n, or f at 240 in this case, would be, you take that 4, this guy, add 1, then take this 1, add 1, and then finally take that 1 and add 1, and this becomes 5 times 2 times 2, so that's 4 times 5, which is 20. So that basically means that there's 20 divisors of the number 240. And define an integer n greater than 1 to be refactorable if it is divisible by f at n. For example, both 6 and 8 have 4 positive divisors, so 8 is refactorable, and 6 is not refactorable. This is because 8 is divisible by 4, but 6 is not divisible by 4. Determine all refactorable numbers n with f at n equal to 6. Okay, so hopefully you understood that. All right, so let me think about it first, actually. Okay, I'm going to actually talk very briefly about that 8 that they gave. 8 is 2 to the power of 3, right? So by definition, if you were to find f at 8, remember you take that guy and you add 1, and that's it, since there's no others. So that's f at 8 is 4. And n is divisible by f at n. So n is divisible by f at n in this case, because we have 8 and we have 4, and that's 2. So this is obviously divisible. So that's what their example is. So hopefully that, I wanted to talk about it really briefly, because otherwise it might seem a little abstract. So now they're saying determine all n's where f at n is equal to 6. Okay? So that means you want a situation again where n divided by f at n is divisible. So we don't know what n is, but n has to be divisible by 6, right? Yeah, n has to be divisible by 6. Okay, so that's a start. Now, if f at n is divisible by 6, I take it one step further here. 6 is what? 2 times 3, right? So that means n has to be divisible by both 2 and by 3. So that means n must equal some power of 2 and some power of 3. You see how I got that there? And if you really wanted to, you could use their notation, the A1. Okay, that's fine. I'll use their notation. N is equal to 2A1 times 3A2. It doesn't really matter, but just to be consistent. Okay, so that's pretty decent. And then, remember, f at n is equal to 6. So if you calculate f at n, remember, you're going to take this first guy and add 1, and then take that second guy and add 1, and they're saying that's 6. So 6 is equal to 1 plus a1 times 1 plus a2. You got it? Okay. All right, so okay, at this point I think it's pretty straightforward. We can either have a 2 times 3 scenario or a 3 times 2 scenario, because you can't have 1 times 6, right? Because one of those would mean a would be 0, and you can't have that, because both of these guys, a1 and a2, have to be at least 1. So a 6 and 0 scenario will not be possible. So that basically means that either a1 is 1 and a2 is 2, or a1 is 2 and a2 is 1. So going back to this, that basically means that n is equal to either 2 to the power of 1 times 3 to the power of 2, which is 18, or n is equal to 2 to the power of 2 times 3 to the power of 1, which is 12. So 18 and 12 are the two possible values of n. Determine the smallest refactorable number n with f at n equal to 256. Okay. All right. So, again, n divided by f at n, that n has to be divisible by f at n, and f at n is 256. And 256 is what? 2 to the power of 8, I believe. 2 to the power of 8. So that means that, I don't know what n is, but n has to have at least a 2 to the power of 8 in it, and then it could have a whole bunch of other stuff. Right? That's the only way n could be divisible by 2 to the power of 8. So that's a very important thing, that n has to have at least a 2 to the power of 8 in it. Okay, so okay, we got to do a little bit of experimentation here because it's not that clear. Let's say n is just one prime number to some power. That means f at n would be, remember you take that first guy, well there's only one this time, and you add 1 to it. And that's it. And f at n is 256, right? So that means 1 plus a1. So a1 is basically equal to 255. So n would be equal to some prime number to the exponent 255. And since we want the smallest, right? Yeah, we want the smallest. I'm going to choose the smallest prime number, which is 2. So this is one candidate for n, 2 to the power of 250. That's very, very huge number. So I don't think that's the smallest. So we got to keep going here. Okay, no problem. Let's just do one more to see. I don't know how many I have to do here. Hopefully not too many. Let's try 2 prime numbers. So we got P1, A1, and then P2, A2, right? Like that. So F at n, and by now, hopefully you're an expert. You take this guy, add 1. Take this guy, and add 2. Oh, sorry, add 1. And then this is 256. And then I guess now you got a little bit more of a choice. Well, I'm just giving an example. So let's say this 256 is, you can break it up into 16 times 16, right? I mean, that's one of the ways of breaking it up. So that would mean that A1 is 15 and A2 is 15 if you did it that way. So therefore, this prime number would be something to the power of 15 and then something to the power of 15, since A1 is 15 and A2 is 15. And then since I'm looking for the smallest refactorable number, I'll choose the 2 smallest primes. So 2 to the power of 15, 3 to the power of 15. And then I guess you have to do a comparison between this guy and this guy to see which one is smaller. And then you just keep going like that. So it's a bit time consuming. But one thing is for sure, that the n has to have that 2 to the power of 8. And that, I think, will limit our choices, meaning we won't have to keep, eventually you'll get to a point where you say it doesn't qualify anymore. Yeah. Yeah, the fact that it has to include 2 to the power of 8. So that helps me, I think, tremendously, because now I'm getting a hang of this, that n, I think, let me think about this, P1, A1, P2, A2, P3, A3, P4, A4, P5, A5. You guys get the hang of it, right? The dot, dot, dot. But F at n is going to be 1 plus A1, 1 plus A2, and so on, right? 1 plus A3, 1 plus A4. So my goal is to make sure that at least one of those A's is at least an 8. Because remember, I've got to have at least that 8. So let's see here. F at n is 256. And let's say I chose 1 for each of these. So A1 is 1, A2 is 1, A3 is 1, A4 is 1, and so on. So far, I've got 2, 2, 2, 2. Yeah. And therefore, this would be, that's 16. So this would be 1 plus 15. Okay, so A5 is 15. So that's good. But let's say if I kept going, like I have 1 plus 1, 1 plus 1, 1 plus 1. I do one more, 1 plus 1. I do 1 more 1 plus 1, and then this one would be 1 plus 8, right? Wait, hold on, 1 plus 7, I believe, right? Because this will be 8 times 2 is 16, and then 16 times 16. Ah, got it. So then this one is a 6, and that would be 7, and that would fail, correct? Because 7 is less than 8, and we got to have at least an 8. So that means that this scenario is the farthest I can go. Yeah. So I hope that made sense. I mean, it's obviously a challenging question, but I think that's how you do it. Yeah. There's a couple I skipped. Yeah, right. I mean, you notice how I did the first two and then I skipped because I think you guys can do the other ones, but this is the final one. So that would make this A1 would equal 1, A2 would equal 1, A3 would equal 1, A4 would equal 1, and then A5 is 15. So my prime number, this guy, would, well, I'm going to choose the smallest prime numbers. First of all, my exponents are 1, 1, 1, 1, and 15, right? And then I'm going to choose the smallest prime numbers. But I'm going to put 2 here because I'm concentrating on the smallest. And then it doesn't really matter. And then 3, 5, 7, the other primes. And then this number, whatever it is, I think it's like 30 million. Yeah. And then you have to compare that number to this number and this number. And there's a couple more. This was 1 prime, 2 prime. This was 5 primes. So there's going to be another number for 3 primes and for 4 primes. There's only 5 numbers that you have to calculate. And then, of course, you take the smallest. And the smallest, I believe, is this guy right here. So that is that one. Show that for every integer m greater than 1, there exists a refactorable number so that f at n is equal to m. Okay, so the first thing I want to do is maybe give an example with some numbers, otherwise it will seem too abstract. Okay, so let's say m is equal to some number. I'm just going to choose 300. I'm just giving an example. First step, of course, is we want to break this up to its prime factors. So I believe it's 2 to the power of 2 times 3 to the power of 1 times 5 to the power of 2, right? So f at m would be, remember, 1 plus 2. You guys know this by now. 1 plus 1 and then 1 plus 2, which is 3 times 2 times 3, which is 9 times 2, 18. Now, I don't know if that was even useful. Because I think we have to kind of go the other way around. We have to figure out f at n equal to m. Okay, so f at n is equal to m. Okay, so f at n is equal to m. So that means f at n so we got to think a little bit differently now. So if f at n is equal to m, and then m we figured out was 300, right? So we got to figure out, I guess, some scenario where you have some numbers that multiply to give you 300. And I guess I'll just keep it simple. I guess I'll just use these guys. So 25, 3, and 4. But then remember, f at n was figured out by that formula. Like, for example, if n was P1A1, P2A2, and P3A3, f at n was figured out by 1 plus A1, 1 plus A2, and 1 plus A3. Right? So that, if you apply to there, if you make this 1 plus 3, 1 plus 2, and 1 plus 24, like that, then if you compare it to there, that means that this is A1, this is A2, and this is A3. So that means that the n would be, and you can use any prime numbers, I'm just going to use the same ones, 2 to the power of 3 times 3 to the power of hold on here. This should have been, no, that's right. 3 to the power of 2 times 5 to the power of 24. Correct? Yeah, I think that's right. So let's figure out f at n again. Just to double check, it would be this 3 plus 1, 2 plus 1, and then 24 plus 1. So that gives me 4 times 3 times 25, which is 12 times 25, which is 300, which is equal to m, which is what I originally had. Okay, so I gave you that sort of numerical example to kind of show that this is possible. Yeah. Now we got to do it in an abstract, well, abstract meaning a letter. We got to use letters now. Because I just gave you one example. We got to show that this is true always. Okay, so let's see what I can do. F at n is equal to m. Okay, so I'm going to use letters now because we got to show it to be true always. So m, let's say, is equal to p1, a1, p2, a2, dot, 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 all the way till pk, ak, right? Because we don't know. Now, this is the part, and we have to carefully figure this out. It's going to be some prime number. It doesn't really matter. I think it doesn't matter what the prime numbers are, but I'm pretty sure, because really, when you calculate f at n, you're only looking at the exponents. So this is the part that's the hardest part here. This is going to be p1, a1, minus 1. And you can look over here to see how I figured that out. And it'll become a little bit more clearer once I figure out f at n. And similarly, p2 or whatever, I'm pretty sure that these don't really matter, but I'm just going to use the same ones. Again, p2, a2, minus 1. And then you just kind of keep going like that, all the way till, I guess, dot, 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 pk to the power of pk, ak, minus 1, like that. Okay, now when you calculate f at n, watch what happens. So remember how to calculate f at n. You take this guy, which is p1, a1, minus 1, and you add 1 to it. And then you multiply by, you take this guy, which is p2, a2, minus 1, and you add 1 to it. And then you keep multiplying that until you get to that guy, which would be pk to the power of ak minus 1 plus 1. Okay, so this all just becomes p1a1 times p2a2 times dot, 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 pk ak. Correct? And that, by definition, is m. See, it's the same as that. So hopefully, when you do one with the numbers, it can help you do this part, which is the more general version of the question.